Hello. In this particular discussion, we will talk about the second problem of RMO 2002. And as usual, we will focus on the big picture and then also talk about the solution of the problem in the process. So, here we have sum of two cubes. Sum of two cubes which is equal to another cube, and we want to find out solutions to this equation where x is a real number. Now let's pause for a moment and look into this problem from a different perspective. We have first cube plus second cube which is equal to the third cube, and immediately this reminds us of the Fermat's last theorem. Now of course Fermat's last theorem is true for only positive integers. Here we are interested in real number solutions, but nevertheless let's give it a try. What does Fermat's last theorem say? It says that a to the power n plus b to the power n equals to c to the power n has no solution, that is no solution, positive integer solution ABC, positive integer solution if n is greater than or equal to 3. Of course, the proof of this theorem is incredibly difficult, and in its full generality it is quite beyond the scope of our elementary number theory discussions. For n equals to 3, however, the proof can be discussed. It uses something called an infinite descent, a method devised by Fermat, but in its full generality the proof requires a lot more than that. But we are just doing this for fun for the moment. In this particular problem, let's suppose for the moment that ABC or these cubes are integer cubes and see how far we can get with this. So we have x square plus x minus 2 whole cube, 2x square minus x minus 1 whole cube equals to 3 times x square minus 1 whole cube, and we are trying to find out solutions. We know by Fermat's last theorem there are no integer solutions, that is a, b, c. If they are integers, there are no solutions, no positive integer solutions to this equation, which tells us immediately that the only way this equality can hold is if one or more of them are zeros. That is, if x square plus x minus 2 is 0, then of course we would want b equals to c. Similarly, if we have 2x square minus x minus 1 equals to 0, then we would want a is equal to c, and so on. So those are the only situations in which there can be a solution. Otherwise there can't be any solution. Question is, when are these pieces 0 themselves? Now pause for a moment here and think about the implication. I mean, this is actually a problem solving strategy. We are trying to guess what the solutions can be, and given an equation, it's always interesting to ask, is there any integer solution? So we are asking a very important question, and we are using a very powerful theorem to make an educated guess. So, and that theorem says in this case that solutions are possible only if each of these pieces or one of these pieces are 0. Now let's look at the first case. Case 1, x square plus x minus 2 equal to 0. So when is that 0? It's very easy to solve. We can prime factorize this. So x square plus 2x minus x plus x minus 2 equals to 0. Sorry, I got an extra x here. So minus 2 equal to 0. So we have x minus 1 times x plus 2 equal to 0. So x equals to 1 or x equals to minus 2. These two values make the first piece equivalent to 0. The only way they will work as a solution if we plug in 1 or 2 into these two pieces and we get the same value. If that happens, that is, if I plug in 1 into 2x square minus x minus 1, let's do that. 2 times 1 square minus 1, which immediately gives me 0. And if I plug in 1 into the other one, 3 times 1 square minus 1, that also gives me 0. So indeed, if I plug in x equals to 1, that works. And that makes all of these three pieces 0, all of these three cubes 0, and immediately that makes a solution. What if I plug in x equals to negative 2? Now that is also very much possible. Let's plug in x equals to minus 2. We have 2 times negative 2 square minus negative 2 minus 1, which is equals to 8 plus 2 minus 1, which is 9. What about the right hand side? In the right hand side we have 3 times negative 2 square minus 1, which is 3 times 3, 9. So they match again. So x equals to 1 and x equals to negative 2 certainly works. This, my friend, gives a very simple yet powerful guessing mechanism of what the solution is. It also tells us a little bit more about how we can actually try to solve the problem. Because you see, in the Regional Mathematics Olympiad, we cannot really use Fermat's last theorem. We can, of course, use it to guess the solutions, and in stronger problems, let's say in INMO or IMO, Fermat's last theorem can be used to make very educated guesses. So this is actually a problem solving strategy. So in this case, using Fermat's last theorem, we not only got a very good guess, we got actual solutions. Let's quickly reframe this problem one more time and try to use our guesses, the ones that we have learned. So we have x square plus x minus 2 whole cube. We have 2x square minus x minus 1 whole cube equals to 3x square minus 1 whole cube. And Fermat's last theorem says, or that particular investigation gave us two solutions, x equals to 1, x equals to minus 2. And x equals to 1 makes all these three things 0, which is very, very useful in this case, because I can take out x equals to 1, factorize it out from each of these pieces. And that is actually very straightforward. We don't even need Fermat's last theorem to find that out. If I factorize each of them, we get x minus 1 times x plus 2 whole cube, because this thing factorizes into x minus 1 times x plus 2. And this one, we can factorize it into 2x minus 1 times 2x plus 1 times x minus 1. So that's also a simple middle term factorization. And finally, the last one factorizes into 3 times x plus 1 times x minus 1 whole cube. So x equals to 1 is not only a solution, it actually it's a solution of order 3. So because each one has x minus 1 whole cube in it. Let's investigate what happens when x is not equal to 1. So if x is not equal to 1, we get x minus 1 is not 0. So we can cancel that off from each of the pieces. So we have x plus 2 whole cube, 2x plus 1 whole cube equals to 3 times x plus 1 whole cube, which is basically 3x plus 3 whole cube. Now, interestingly enough, these two pieces, x plus 2 and 2x plus 1, they add up to give you 3x plus 3. This is a critical observation. These kind of observations actually make or break a problem. So if you look into this, you'll see that x plus 2 plus 2x plus 1, this gives you 3x plus 3. So we can exploit this particular result and write it like this. So x plus 2 whole cube plus 2x plus 1 whole cube equals to x plus 2 plus 2x plus 1 whole cube, and we can use the a plus b whole cube formula to expand this. So x plus 2 whole cube, 2x plus 1 whole cube plus 3 times x plus 2 times 2x plus 1 plus, okay, let's multiply this, x plus 2 plus 2x plus 1. So basically I used a plus b whole cube equals to a cube plus b cube plus 3ab times a plus b, this formula. Okay, so now we can cancel off. So let's bring this part down, x plus 2 whole cube plus 2x plus 1 whole cube. So we can cancel off these two things and we are left out with this piece in the right hand side and 0 on the left hand side. So what do we have? We have 3 times x plus 2 to x plus 1 and 3x plus 3 equal to 0. Now immediately we get each of these pieces, these are 3 possibilities, each of these pieces can be 0. So x plus 2 equal to 0 gives me x equals to negative 2, which was actually our first guess. We guessed it using Fermat's last theorem. We already have x equals to 1. We now have x equals to minus 2. From this factor we have x equals to so if we said 2x plus 1 equal to 0, we get x equals to negative half, and if we set 3x plus 3 equal to 0, we get x equals to minus 1. So we actually get all the 4 solutions, x equals to 1, x equals to negative half, x equals to negative 2, negative half, x equals to minus 1. And they are all solutions because they are the only solutions because this is a, if you look into this, this is a 6th degree polynomial. 3 times 2, the highest power is 6. So it's a 6th degree polynomial. It will have 6 solutions, and x equals to 1 will repeat 3 times because we could factor out x minus 1 whole cube. So we have all the solutions here. Let's revisit the big picture one more time, the problem solving strategy that we actually found. The big picture is this, that even when real solutions are demanded, it's often useful to find integer solutions, maybe then rational solutions, and then to its full generality real solutions. And one may use tools like Fermat's last theorem, which are very heavyweight tools, but tools indeed, to make educated guesses. Of course, then we have to establish and use those guesses to finally pin down the solution of the problem. Thank you for watching this short discussion. We will meet you in another discussion in another video. Thank you.